And if this works, it's going to be bigger as well. And if this works, then we have a full system which should be scalable to power plant size. So the aim of that project is to actually show scalability. The commissioning of Novatron 2 is planned for 2028, I believe. So I would say if we manage to succeed, that we will manage to have commercial fusion power within the next decade.
So yes, you heard it right. We are just a decade away from a commercial nuclear fusion deployment. A lot more interesting insights coming your way on this episode, so stay tuned. Hello and welcome to yet another episode of the Mission Shunya podcast, Conversations towards the global zero carbon transition. First things first, I hope you are doing well. If you have been following this nuclear energy series, you'll know we have already explored the basics of nuclear in Nuclear 101, dug into the myths and facts with Radiant Energy Group, gone behind the scenes with World Nuclear Association, and even heard from a fusion startup, Renaissance Fusion, about how Europe is pushing the frontier of science and innovation. Most recently, we also discussed probabilistic risk assessment, highlighting how risk is managed in nuclear systems. Each of these conversations has opened up a different lens on nuclear, from safety and perception to global policy and cutting-edge fusion research. And today, we continue that journey with another fascinating perspective from the fusion world. Unlike the big government-backed projects that dominate headlines, Novatron Fusion, a Swedish startup, is taking a radically different approach, rethinking how magnetic fields can be used to confine plasma and bring fusion closer to reality. In this conversation, we get into the technical side of fusion, why Novatron's approach stands apart, and what it means to build a career in one of the most ambitious clean energy fields of our time. So, to discuss that, who is our guest and what is her role at Novatron Fusion?
My name is Katarina, and I work as a computational physicist at the Novatron Fusion Group. My mainly task is to work with simulations of the plasma, and I also help designing our next experiment, the Novatron 2, where we're going to see if our concept is scalable to power plant size.
So, first things first, when I try to reach out and know more from experts in the nuclear fusion space, there are not many people around. So you being in this space means that this is a special place and something must have really drawn you into this space. Can we start with looking at your background and what actually drew you to nuclear fusion? Was this like a big passion project of yours, or what actually drew you into this?
So my background is in research. I first in experimental particle physics and later in cognitive and computational neuroscience. And then I worked a couple of years in industry with applied machine learning, but I missed physics so deeply. And on the other hand, I didn't want to go back to my research field since I really wanted to feel like I worked with something that really mattered, like that I felt really mattered, and not only to a few people. And then I started thinking about fusion because it's super cool, obviously, and has a lot of impact. And I did some research on it, and I was amazed by how much had happened within the last years. So what had felt like more like science fiction when I was an undergrad now look really promising. And I think the most crucial event in the fusion landscape, I think it's that it has broadened in the past 10 to 15 years. Especially when it comes to private initiatives. And as an indicative example, the number of private initiatives has increased from 5 in 2010 to almost 50 in 2025. And let me explain why this is important.
Sure.
So there are several different approaches to fusion, where the most important ones can be divided into two general approaches, inertial confinement and magnetic confinement. So in inertial confinement, the fuel is in the shape of small pellets, and they're being heated and compressed by lasers. And I'm not sure if you've heard about the NIF in the US, for instance. So it's just basically you have very strong lasers and you beam this into a pellet and then you compress it and then fusion happens for a short time. But in the other approach is called magnetic confinement. And there the plasma is confined using very cleverly designed magnetic fields. And the heating is carried out by, for instance, microwaves. And historically, the magnetic confinement approach has been dominated by an approach called tokamak. And this is mainly due to politics and like the funding being focused in this way. However, scientifically, to be honest, no one really knows which concept is going to be the most successful, like as a full-scale power plant. And this means, now I'm coming to why it's important, that the number of concepts being researched, I think, correlates heavily with the probability of success for a fusion as a future energy source.
So is the physics problem the main thing that actually drew you into the field?
Yes. I mean, there are two things. One, that it has an enormous impact if it succeeds. And the other thing, that the physics is so complicated that I get to feel stupid every day, which I love, which means I'm learning new things. And that's super cool. I love that.
Fantastic. Now let's talk about Novatron. So what is the key USP of the company in your own words?
So to understand that, I think I need to go into some background again. So Novatron is part of the same family as the tokamaks that I mentioned before, and also something called stellarators, which people might have heard of. I don't know if you've heard of it, but they're all magnetic confinement. So in this case, we don't have any pellets or anything. We have a super hot gas. It's called a plasma, and it's actually on the order of 100 million degrees. So hotter than the sun, like the surface of the sun at least. So that's super cool. And this needs to be confined in order for fusion to happen. And as you can imagine, like keeping this plasma in place is not an easy task. Hot gases naturally want to find equilibrium, meaning it wants to spread out into the colder surroundings. So we need to be really clever about how to confine it, because any material you can think of would just melt. So the idea with the magnetic field is based on the fact that charged particles are affected by magnetic fields. And in a plasma, the nuclei are separated from the electrons. So we have two populations of charged particles, which we can then manipulate with our customized magnetic field. And the shape of this field is what differentiates tokamaks and stellarators, so the other concepts, from each other, and also from Novatron, which has another magnetic field. So if we look at the fields, the main difference is that the field lines, those are the virtual lines like showing the direction of the magnetic field, they're closed in a tokamak and stellarator. So they're circular-ish, and the plasma is in the shape of a donut. I'm sure if you Google fusion, this is what you will see. You will see like a donut-shaped plasma. But the Novatron belongs to another group of magnetic fields, which are called open field lines. So they look more like a two-necked bottle. I don't know if it makes sense to like describe this because you can't see my fingers, but like if you have a bottle, then you replace the bottom for another neck, so you have two necks. And then you can imagine the field lines like going along the bottle from one neck to the other and like gathering at the necks and then spreading out outside the bottle again. So it's like the field lines spread out and they don't come back to the device. And then you wonder, why does this matter? And that's because the charged particles, they mainly follow the field lines. So maybe you then think like, it sounds like a bad idea to have open field line system, right? Like the particles can escape through the necks. But that's correct. Even though like the shape of the field lines in the necks, we call them mirrors, those necks, then they make actually most of the particles bounce between them and thus be confined. But they also do like leak out. Part of the particles will definitely leak out. And that is one of the biggest challenges for open field line systems. But there are also huge advantages. For instance, open field line systems can run continuously, which tokamaks can't. And this is obviously very beneficial for running a power plant that it can run without having to stop all the time. And compared to stellarators and tokamaks, mirror machines are also very simple in design. The magnets are just perfectly circular coils, which are easy to scale industrially. Stellarators and tokamaks, they require magnets with a quite complicated shape, which also means there's a lot of mechanical stress on the magnets to deform when they're in place.
I'm sure we can definitely visualize, and I will make sure that I will leave some images for reference in the blog post for this episode, definitely. So, if I understood this correctly, the key USP is then creating this magnetic field in a unique way. Is magnetic field the key component in is that the biggest bottleneck or the biggest physics challenge that is kind of holding us from progressing in the nuclear fusion space?
I would say for magnetic confinement, yes. So maybe we need to go back a little bit to the basics again. So there are basically three things you need for fusion. You need high density, very high temperature, and then you need to maintain these conditions for as long as possible. So heating the plasma this is basically an engineering problem. You can just heat it but you can heat it with microwaves, for instance. But the other thing to keep it confined is very hard because it's very hot and it's very high density. That means it's very high pressure. And again, it wants to spread out, and we must apply external forces to push it back. And this is extremely challenging for all the systems. And depending on what kind of fusion system you have, the way it tries to escape are different. But the shape of the magnetic field is one of the most important things to push it back. If you want, can go in a little bit more into how the plasma can escape.
Yes, that'll be good to know about the importance of plasma being confined in the space. So is the main USP for Novatron around creating the magnetic field? Are there other challenges or problems that you are actually working on that is also very interesting?
Oh yeah. Okay. So I think the most fundamental issue is to keep the plasma in place, and that has to do mostly with the magnetic field, but also with other techniques that I can describe. But let's just go into first why it's so hard to keep plasma in place. So like we said before, it's very high density and high pressure, which means it wants to spread out. And we have to apply external forces to push it back. So the plasma can get very creative, let's say, in its attempts to escape. But for simplicity now, we can focus on open field line systems. We can divide its escape attempts into instabilities and loss. So instabilities, they grow in the plasma itself, typically due to gradients, for instance, in pressure or temperature distribution. And then eventually it will cause the plasma to escape from the device or move into the vessel wall even. And historically, mirror machines have suffered from radial instabilities called MHD instabilities. And this is due to the shape of the magnetic field itself. So the Novatron magnetic field is redesigned. The shape is redesigned so to stabilize against these instabilities. So this is the USP. Maybe this is actually answering your last question. This is the USP of the Novatron to stabilize against these instabilities. And then the other escape attempt is axial loss, which means that they're escaping out through the necks that I've described before. And to mitigate this loss, we're combining two other established techniques to push back the particles. And this is not part of the magnetic field. One is called ambipolar plugging, and then we use an electrostatic field pushing on the ions, but it's actually built up by the plasma itself. So it's quite cool, but it has nothing to do with the magnetic field per se. And then the second method is called ponderomotor plugging, and then we're using an oscillating electromagnetic field, which act on both electrons and ions. And that also has nothing to do with the magnetic field per se, even though, the shape of the field and the coils and everything will obviously make it more easy or more difficult to place the electrodes, etc.
Fair. A lot of interesting stuff. Now, in the journey of Novatron, when we talk about nuclear fusion, one key question is always, how far are we from actually seeing the commercial use case of the technology? But I think we should actually take a step back and ask about what are the incremental progress that we are seeing in terms of technology development. How is the roadmap for Novatron? What are your key milestones that you have achieved? And what are the upcoming milestones in the journey?
Good question. So like I described before, we're focusing on confining the plasma So because heating it and creating it is an engineering problem that people have solved before, basically. So we just trust our engineers that they will do the job. So our roadmap focuses on showing or validating that our approach to confining it works. So we're doing this in different steps. The first step is to show that the plasma is stable due to the magnetic field shape. And we're doing that by building a smaller experiment. It's like 4 meters tall. That is actually up and running since this winter at the Royal Institute of Technology in Stockholm. And the aim of this machine is just to validate the stability of the magnetic field towards these MHD instabilities. But then we're planning in the next step, we're already planning the next experiment, which is called Novatron 2. We're not so creative with the names. And this will test the techniques that I mentioned to mitigate the axial loss, so the electrostatic field and the ponderomotive, these oscillating fields. And if this works, it's going to be bigger as well. And if this works, then we have a full system which should be scalable to power plant size. So the aim of that project is to actually show scalability. And the commissioning of Novatron 2 is planned for 2028, I believe. So I would say if we manage to succeed, that we will manage to have commercial fusion power within the next decade.
Wow, that is very promising to hear. You did mention a word, trust. And from what I understand from reading or researching around what's happening in the fusion space, a lot of players, companies who are starting up are also clearly mentioning that they are actively collaborating or working with peers in the industry just to ensure that you hit the commercial target ASAP. Is it true for Novatron as well? You are based in Europe, but are you collaborating with others around the world?
Sure, it's extremely important to us to stand on the shoulders of giants, because it's super hard and there's so much research which has been carried out before and shouldn't be missed, right? So we have, for instance, collaborators in the US. They're old and have been working with mirror machines since the 70s and 80s, and they can quote, what people said in the 80s and what they did wrong and which mistakes we shouldn't repeat. They're also helping us to develop the inventions that they made at that time. Then we have a really nice feature that we're working with in Japan, where they did this ponderomotive experiments in the 70s. So then we were drawing on his knowledge there. We're starting up collaboration with Princeton and MIT, with, of course, KTH, the Royal Institute of Technology here in Stockholm, with UKA. We can't afford to not, collaborate with people who know more about fusion than us, or know about fusion in specific areas where we don't have expertise. So definitely.
Perfect. That's actually very good to know that you're working on same lines as well. But going further, when you actually talk about fusion and when you actually pitch it to investors and getting money on board, what are the other storylines that you bring to the narrative? How do you kind of pitch? Because when we generally speak about nuclear energy, there is always a lot of skepticism and actually probably to an extent a large part also activism. But when you pitch nuclear fusion, and with especially being a little further down the line in terms of commercialization, what are the narratives you generally bring to the storyline?
So usually we have to distinguish ourselves from fission because we claim to deliver, a very high power base load, very reliable and very efficient in everything. So, and with a high energy yield. And then we mention the word nuclear, and then everyone's like, is it fission? So we usually have to just stress that there's no long time radioactive waste and there's no risk of core meltdown. So the quantity of fuel present at any time in the reactor is enough only for a few seconds of operation. So there's no risk of chain reaction. So those two things are righteously the things that people are most worried about when it comes to fission. And then obviously we stress that it's fossil free, but that's true for fission as well. But these things together, maybe also together with the fact that the fuel is we can get it from proper from regular seawater, even though it's kind of a half truth because the most efficient reactors use deuterium and tritium. And tritium we need to breed in the reactor, but people are developing that technique. But it's not this like radioactive uranium which you have to destroy the landscape to get and all of that. So I think that's mostly what we pitch, that it's fossil free, that it's very reliable, but it's not fission.
Fair. And that's a good storyline, actually. But the other question that I generally ask or generally want to know, because even in terms of nuclear fission, scaling up globally has been a key challenge. And different countries, different regulators have their own set of checks and process to kind of help or implement nuclear energy in their own regions. In terms of nuclear fusion, I'm sure you would have thought through this. How do you plan to scale across based in Europe? Getting it developed in Europe might be easy, but the commercial value propositions will only happen when this can be scaled globally. Any indications or any thoughts on those lines?
I don't think it's my main area of expertise, but I would say that it's interesting if I can just speculate. It's interesting to see that both, across the world, fusion is being researched and developed. There is a big fusion research facility in China. I think there are several actually, in Korea, in Japan, in Russia. They're great with mirrors. In the US, obviously, in Europe. And those are the ones that I know. I think there's one in New Zealand as well. So it's kind of spread out across the world, which makes it easier, obviously, for regulators to adjust. But when it comes to regulations, I think it's going to be one of the biggest challenges in Europe to start with. And I don't know how it would work across the world, if it would be easier or harder.
On similar lines, let me ask a equivalent question for someone who's working in this deep tech. How easy or how challenging is it for you to kind of get the right talent pool, get the right technical support for this emerging technology?
Oh, that's a great question. For instance, look at me. I have a weird interdisciplinary background. I'm not a plasma physicist. I have a PhD, but it's in another, even if it's related, it's in another physics field. So that's kind of telling that they couldn't find anyone better. No, but seriously, it's hard to get people who have a research or industry background in fusion. It's extremely hard. What you can get are people like me who are physicists and have a solid research background, but maybe not in fusion. So now we're talking about, developing the concept, understanding the theory, all of those things, which is the department that I work in, the computational physics group. So for us, it's really hard to get people with like real plasma and fusion experience. We're looking internationally though. And we have been able to recruit people internationally, and even more, like the bigger we get and the more. Now we had a publication being published in nuclear fusion, and those things always help to spread the word and to make people understand that we're a serious agent, etc. So it's much easier now. We have a lot of people like reaching out to us. But then when it comes to the engineering side, it's a little bit easier because there are so many specialties where people actually can draw from their knowledge from other fields like electronics or experiment control or just mechanics or things like that. But then we have this specialized knowledge of like how to measure and diagnose plasma, and that's harder. But I think people are doing a great job at learning this new field and, using their experience from other fields and trying to apply what they've learned before and then just be open and curious and learn. But yes, the short answer is it's hard.
As expected, I would definitely expect that. Now, moving on, Katarina, you've been very sportive and very kind to kind of explain the big concepts in a very simple way. So it's good to kind of ask a few rapid questions. What would you kind of say if there is one myth about fusion that you wish like more people understood clearly?
I would say that it's not fission. So just to repeat what I've said, that it's not this radioactive waste and no like core meltdown or chain reaction. I would say that's or perhaps actually that it's always 30 years away. I think it was a researcher in the 80s who accidentally said that, and it's been quoted so many times, but it's not anymore. And I hope that people will change their minds about fusion and realizing that even if it's still in a research phase, like we're going to solve it. If it's not us, it's going to be someone else, and we're going to collaborate across the fusion community, and we're going to solve it together.
You would be surprised if I were to tell you that I was in fact going to ask you that as my follow-up question. Is the fusion being 30 years away is the biggest misconception in the space?
I think you're perfectly right.
That is good to know. And I hope a lot of people who listen to this will feel more optimistic after listening to what you had to describe in detail. So that brings me to the next question. Like, what is the biggest hope that you have seen having worked in the space for quite some time now and coming in from an interdisciplinary field and allied field, but now that you are here getting your hands dirty in a way, what has given you optimism about the space?
It's a hard question. It's a combination of a lot of things, but maybe two things mainly. And one is actually how my experience is that the general audience and policymakers start noticing fusion and start appreciating the potential. A couple of years ago, when I started my job, no one knew, including my mom, didn't know what fusion was. And now when I talk to people, I always ask them, like, I work with fusion, do you know what it is? And I would say 75% say yes. Maybe they don't know exactly what it is, but they know kind of you take the sun down to the earth and try to generate a star on earth and etc. So that story, at least they know like the basics. And this is obviously needed for us to be able to get these regulations going and etc. So that's one of the things that gives me hope. And the other thing is how open-minded and solution-oriented the fusion community is. For instance, like many have identified how machine learning can help with stabilizing the plasma in real time, or like how they use machine learning to design advanced magnetic fields, and also how we can make use of new techniques, for instance, high temperature superconducting magnetic tape, and just like trying to use the latest or old techniques to combine them just to get it to work.
That's interesting. I like the way that you're thinking about sun and talking about that. That was how even I learned about nuclear fission the first time around. So it is good to know. A final question on this lines. What is an advice that you would probably give young researchers or engineers who would like to work in this field? We touched upon this briefly, but what would be one key advice?
Oh, please come to us. I would love for people to, obviously they should always take courses and classes about things that interest them. Obviously, that's my first advice. But if you want to go into fusion, just take classes about plasma physics. And there are so many fields within fusion which you can focus on. You can be a simulation person, and then you can work with me. Or you can be an engineering person, then you work to characterize the plasma. So it's more engineering focused. You can be a theorist. I also work with theory to try to understand, like predict what's happening with the plasma. I guess those are the fields that are most like fusion specific. Then obviously, if you're interested in mechanical engineering, you can also like help out designing the vacuum vessel. What else? It's always good. Machine learning and programming is always great for any engineering field, I would say. And it's great if you want to work with fusion, because we need to simulate the plasma. We need to do advanced statistical analysis on the plasma to characterize it, because we can't just go and measure it. We measure it very implicitly, and we have to make a lot of inferences. So statistics, programming is always a great background to have, whatever field you're in, and fusion specifically.
Well, one thing for certain is that people who are technically inclined or who have research-oriented interest, I think will definitely find this conversation really interesting. Now, on a final note, if I were to go back the question around Novatron's roadmap, you did mention 2028 is one key milestone that you're looking forward to. Any other milestones, or when can we actually realistically see a fully commercial product solution from Novatron?
We usually say internally and externally, I think, that we want to do it within the next decade. So, I don't know, 2039 and a half, perhaps, would be it would be super cool to have it before 2040, to have a commercial power plant by then. And I think it's feasible.
Fantastic. Katarina, it's been an absolute pleasure to have you on the conversation. And I'm sure a lot of people will kind of agree with me when I say this, that we learned a lot about nuclear fusion in this conversation, more than what we could actually read and understand. So thanks a lot for taking time to join me on the podcast and share your experience in this.
Thank you so much for inviting me. It was super fun to participate.
That was Dr. Katarina Bendtz giving us a fascinating look into Novatron's unique approach to nuclear fusion. We spoke about the technical challenges of fusion, the complexity of plasma behavior, and how Novatron is working on innovative confinement strategies to overcome some of the biggest barriers in the field. Katarina also shared what it's like to pursue a career in fusion research and why Europe's growing fusion ecosystem gives her optimism for the future. This conversation reminded us that fusion is not just about solving physics problems. It's about persistence, innovation, and the people driving the science forward. And as we come towards the end of this special nuclear energy series, only 2 more episodes remain. Up next, I'll be speaking with a special guest on how nuclear can sustainably power the AI revolution. A timely discussion as energy demand surges with the growth of digital technologies. If you have any feedback, missionshunya@gmail.com is our ID. Thanks for all your inputs as always. So until next time, this is Girish Shivakumar signing off, and as always, thank you for listening.